Okay, this is a presentation on adaptive blind channel estimation in OFDM systems. My name is Aniruddha Kalya, UFID 391919976. I would like to start with the basics of OFDM. It stands for orthogonal frequency division multiplexing. The concept behind OFDM is uh, uh, different symbols are sent over different frequencies, and these frequencies are harmonically related to each other so that they are orthogonal to each other. These frequencies are termed as subcarriers in OFDM terminology. The advantage of them being orthogonal to each other is that it brings a robustness to the intersymbol interference caused by the channel. OFDM transmitter can be explained as the data generator produces symbols to be transmitted, which is then converted into blocks of data by the serial to parallel converter, then sent to the IDFT block, which essentially modulates different subcarriers using these message symbols B1 to B capital N. Then either cyclic prefix or zero padding is done, which is later on sent to a parallel to serial converter for transmission over the channel. I will discuss about cyclic prefix and zero padding in the next slides. The main advantages of OFDM are it has very high spectral efficiency. Again, because we will be using multiple subcarriers, and these subcarriers being orthogonal to each other will result in mitigation of intersymbol interference. And it is very simple to implement because modulation of symbols over different subcarriers which are harmonically related can be done using a simple IDFT transformation matrix. Now, because the subcarriers are orthogonal to each other, we can observe that OFDM will give a robustness to frequency selective fading, because if over one subcarrier there's SNR of the channel is less, we can send less bits over that channel and more bits over the subcarrier where the SNR of the channel is high, hence balancing out the effects of fading and bringing about a robustness. Now, to discuss about the cyclic prefix and zero padding, we have to first understand what guard interval means. Because in practical systems, the subcarriers which are generated by local oscillators are not perfectly orthogonal to each other, and the channels are highly dispersive in nature, especially the wireless channels, will lead to intersymbol interference, although the carriers are almost orthogonal to each other. So a solution to this problem is providing a guard interval in the transmitted block of data. So what can be sent over the guard interval? We have two methods in that. One is cyclic prefix method and the other is zero padding. In cyclic prefix method, as shown in the figure, we have the guard interval being filled with data that is taken from the first few elements of the block, and so the entire OFDM symbol will have the block of data appended by the initial part of the block of data. In zero padding, it is pretty straightforward, where we zero pad the data with essentially 0, therefore we send nothing over the guard interval. Zero padding being a simpler technique is gaining more popularity, and main reason behind it is its simplicity. In this project, I have employed zero padded OFDM system. So again, discussing the transmitter part here, after the modulation using the IDFT block, we zero pad the vector x to get the signal to be transmitted. So x of n is generated as given by this equation. X of n is fh and the zero vector multiplied with b of n, so that we will get the modulated part as well as the zero padded part. F is nothing but the IDFT matrix given by this, where Wn are twiddle factors or sinusoids, and After transmission, the received vector is given by y, which is h f into b plus w, where w is the noise added by the channel, and in this we have taken it the general term for the variance of the channel is taken to be sigma square. Here in the receiver part we will remove the zeros remove the data from received vector uh, corresponding to the zero padded length. So hence we get this kind of formulation where h itself has zeros padded to it, and hence the size of vector y will be the same as size of vector b. So generating 128 symbols using MATLAB, we get this following diagram, and this is a constellation diagram of the modulated data. QPSK modulation is used for this purpose. This is the quadrature axis and this is the in-phase axis. We see that all the symbols lie in either minus 1 plus j0 or 0 plus 1j or 1 plus j0 or minus j plus 0. So after modulating it using the IDFT matrix, we get the signal to be transmitted as shown by this figure. We see that this has a mixture of large number of sinusoids, hence exhibiting a sort of periodicity. This is the received constellation diagram. This is still in the modulated phase. We can see that due to the noise added by the channel, the symbols are scattered all over the place, but using a detector we can segregate them into either on the horizontal axis or the vertical axis according to the input modulated constellation. Now coming to channel estimation. Channel estimation is particularly important because the knowledge of the channel will affect the link budget analysis in a in a major way, because the entire link budget analysis will assume certain characteristics of the channel and then perform. So the entire economics of the telecommunication is dependent on how good the estimate of the channel is available. So there are two types of channel estimation techniques which are popular: supervised techniques and the unsupervised or the blind channel estimation techniques. In this project I'll be focusing on the blind channel estimation, and I've assumed the channel length to be a maximum of L plus 1, where L is the number of symbols that are zero padded, and blind channel estimation basically means that the channel edge is estimated using only the received data and we do not have any training pairs. The fundamental technique used in this project for channel estimation is the subspace approach. The main assumption in the subspace approach is that the received data autocorrelation matrix is available, or while doing simulations we'll have an estimate of the received autocorrelation matrix, and we have to segregate the received signal into its uh, constituent subspaces, uh, estimating the signal subspace and noise subspace, and we have to recognize that signal subspace is spanned by the columns of H, so that the crux of the problem is to find the signal subspace and one of the basis vectors of the signal subspace. So again, revisiting the received signal equation, we have the received signal y of size n plus L, that is total block size plus the zero padding size. The received autocorrelation can be defined as expectation of the output vector into the Hermitian of the output vector, which will give us h into h Hermitian plus sigma square into identity matrix of size n plus l by n plus n. Now decomposing this autocorrelation matrix, we can observe that there will be n plus l linearly independent singular vectors because the autocorrelation matrix is Hermitian and positive definite, and observing it more we can recognize that we can have n linearly independent vectors corresponding to the n highest singular values which will form a basis for the signal subspace, and the L linearly independent vectors which correspond to the L least singular values forming a basis for the noise subspace. So this slide basically explains that columns of H are equivalent to the highest n singular vectors obtained by decomposing the autocorrelation matrix, which will form a basis for the signal subspace, and because there are n linearly independent vectors, the dimension is n, and the L singular vectors corresponding to the L least singular values of the autocorrelation matrix will be equivalent, will form a basis for the noise subspace, and the dimension is L. So now the problem can be reduced to determining the first column of matrix H using an adaptive method or an iterative method. You have to observe that the noise subspace is complementary to the signal subspace. What that means is the basis set Hermitian into the signal basis set of signal subspace will give you a zero. The inner product of every vector from the signal subspace with every vector from the noise subspace will give us a zero. So considering V belongs to the noise subspace, we will have V Hermitian into H. We will have V Hermitian into H equal to 0. Now because R is Hermitian, we can write it as H transpose into V conjugate being equal to 0. So now because H transpose V conjugate is 0, we can form a sum of these elements for every V and obtain a W matrix written as follows. That is Vi into Vi Hermitian, summation running from I equal to 1 to L. Now this equation H Hermitian into W into H will be 0 because H transpose into V star is a 0, and hence we can conclude that small h, which is nothing but the impulse response of the channel, is the singular vector corresponding to the least singular value of the matrix W. Now we have to notice that capital V is a Hankel matrix of this form where VI's, the individual VI's, belong to the noise subspace. So finally, the problem is finding the singular vector corresponding to the least singular value of the matrix W. W is formed by a linear combination of Vi into Vi Hermitian. Now the problem of determining UW is considered, where UW is the basis for the noise subspace. So we have to obtain the vectors UW which will form the basis for noise subspace, and later we can form the matrix W by which we can do singular value decomposition and obtain the impulse response estimate H. This is done using a method called orthogonal iteration, which basically can be stated by the following lemma. If Q is a symmetric positive definite matrix of size k, with singular values being S1 to Sk in decreasing order and Fi's being the corresponding singular vectors. If the sequence z of k, if the sequence z of k, where z of k itself is a matrix of dimension k cross l, is defined by either of the two iterations given here, z of k equal to orthonorm of q inverse into z of k minus 1, z of k is equal to orthonorm of I minus mu into q into z of k minus 1, where mu is greater than 0 and less than 1 over s1, and I is the identity matrix. Then, as k tends to infinity, we will get the singular vectors corresponding to the least L singular values, provided that the matrix Z Hermitian of 0, that is the initial uh, guess of the matrix Z, Hermitian of that, into the least into the singular vectors corresponding to the least singular values is not singular. So the determinant of Z Hermitian of 0 into Fk minus L plus 1 to Fk should not be 0. If this condition is satisfied and one of these two iterative techniques is used, then as k tends to infinity, we will get the sequence of matrices to be the singular vectors itself, corresponding to the least L singular values. So using this technique, we will solve the problem of channel estimation. Now, solving problem 1 is pretty straightforward, assuming that UW is available, that is the noise subspace basis is available. We will use orthogonal iteration to determine H, which will be nothing but a simple normalization equation given by h of n is equal to h of n minus 1 minus mu of n to w of n into h of n minus 1 divided by the norm of the same, where v of n is 1 over trace of the estimate of the w matrix. This is a standalone update equation applied once every iteration. So once we get w every iteration, we will apply this to get a new estimate of the channel. Now the thing is, we have to first determine the basis for the noise subspace and later form W. So this slide will explain the LMS based approach to obtaining an estimate of the basis of the noise subspace, that is UW. Using equation 2 in lemma, that is z of k is equal to orthonorm of I minus mu q into z of k minus 1, we can form a parallel to solve this problem, where where A is replaced by the instantaneous estimate of the autocorrelation matrix, which is y of n into y of n Hermitian, and when that is done, we will end up with this equation for the updation of u of w. S of n here represents u of w, u subscript w. S of n is equal to orthonorm of I minus mu by norm of y of n square to y of n into y of n Hermitian, where this is the autocorrelation, and S of n minus 1, which is the previous estimate of u subscript w. Now, the important thing to notice here is that this orthonormalization is carried out using QR decomposition. Second approach to this problem, that is the problem of determining the basis for noise subspace, can be done using the recursive least squares approach, that is the RLS approach. And using the equation 1 of the orthogonal iteration lemma, that is S of k is equal to orthonorm of A inverse into S of k minus 1. And if we substitute A as the memory weighted estimate of R, that is R of n is equal to summation I running from the first from the initial point up to the current iteration, gamma to the power n minus y into the instantaneous estimate of the autocorrelation matrix, that is y of I into y of I Hermitian, we will end up with this update equation for u subscript w, that is s of n. It is orthonormalization of p of n into s of n minus 1, where p is nothing but r inverse. So here the forgetting factor gamma, which ranges from 0 to 1, will indicate how much of weightage should be given to previous estimates of the autocorrelation. If gamma has a value such that this term gamma to the power n minus I is decreasing with I, then the current instantaneous estimates will get lesser weightage when compared to the initial estimates of the autocorrelation. And if it has an increasing pattern, then the previous estimates of the autocorrelation will get a lesser weightage when compared to the current estimates. Now, implementing this in MATLAB with number of symbols generated by the data generator being 6400, the modulation used being quadrature phase shift keying QPSK, the block size being 64, that is the size of the IDFT matrix being 64 by 64, the length of zero padding being 16, that is the final transmitted sequence will be of length 64 plus 16, 80. The SNR of the signal after the noise is being added is 30 dB, and the channel to be estimated is this, minus 0.5546 minus j 0.2138, 0.1604 minus j 0.6356, 0.4008 minus j 0.2904, 0.3161 minus j 0.1138. The reason for choosing this channel in specific is that it exhibits frequency selective fading and it is complex in nature. Using LMS algorithm, we will get the following plot for the mean square error versus the number of iterations. So we see that as number of iterations increases, the mean square error decreases for every constant, for every impulse response component. That is, h of 1 follows this mean square error plot, h of 2 is given by the red curve, h of 3 is given by the green curve, h of 4 is given by the black curve. All of them seem to converge to a stable point, and the final estimate of the channel obtained is 0.13 minus 0.27 minus j 0.39 minus 0.49 plus j 0.01 minus 0.52 minus j 0.25. Using the RLS algorithm, we will get the following mean square error plot. Even here, they exhibit a similar pattern. H of 1 is shown by the blue curve, h of 2 by the red curve, h of 3 by the green curve, and h of 2 by the red curve, h of 3 by the green curve, h of 4 by the black curve. Here we see that the maximum mean square error is less than compared to that of LMS technique, which is slightly greater, closer to 0.25. Here it is, the maximum is slightly greater than 0.2. Performing the singular value decomposition operation using the standard conventional singular value decomposition technique, we obtain the following mean square error plots for every component in the channel impulse response. We see that the convergence is very noisy because there are inverse matrix inversions involved in this algorithm, which will require a matrix to be non-singular, and there are regularization factors in every iteration, which causes this noisy convergence pattern. While the final estimate obtained is shown here, minus 0.25 minus j 0.37 minus 0.27 minus j 0.39 minus 0.49 plus j 0.01 minus 0.52 minus j 0.25. We know that SVD algorithm is highly complex, which is of order cube. Here we compare the complexity of LMS and RLS mainly. Complexity of RLS will come up to be a total of n plus L whole square into L, where n is the block size and L is the length of zero padding. Complexity of LMS will come up to n plus L into L square. So we see that RLS has higher complexity when compared to LMS because usually the zero padding length will be small when compared to the block size. When comparing the performance of LMS and RLS, we can conclude that LMS performs better when speed of convergence is a concern, but RLS performs better when accuracy of convergence is the concern, because RLS has a better estimate of the autocorrelation matrix, but LMS gives you a faster estimate of the autocorrelation matrix. These differences will make these algorithms work as shown. Now, demo of the simulations will be shown. This is the code which is used to simulate the LMS based approach for channel estimation. So the number of QPSK points that will be given by 4. Number of data points chosen is 6400, and the block size is chosen to be 64. Zero padding length is chosen to be 16, and these these lines correspond to generating the QPSK modulated data and plotting them. So we reshape the matrix so that we will get block blockwise. We will get the data blockwise, where block size is 64, and we zero pad the data in this line, where every vector is zero padded by zeros of a vector of zeros of length L. So this is the channel to be estimated: 0.5546 plus 0.1604, 0.1408, 0.3161 minus J.2138, 0.6356, 0.2904 minus 0.1138. Topliss structure of the channel is obtained in this equation. Now the modulated data is passed through the channel in this equation, and additive white Gaussian noise is added in this equation at an SNR of 30 dB. Now this part of the code will concern with the channel estimation. The impulse response estimate matrix is initialized randomly with uniform random distribution. The autocorrelation matrix is also initialized randomly. Here the instantaneous estimate of the autocorrelation is obtained, and here the QR decomposition is performed, and this part we can see that this part corresponds to the LMS based approach, and this part is constructing the W matrix using every vector obtained in the basis for noise subspace, that is U subscript W, and this is the impulse response estimate that is obtained by normalizing the vector as shown in the slide. By storing the error values and plotting the mean square error, we will end up with the following graphs. So these are the dense transmitted data symbols. These are All these data symbols are modulated into either of these 4 points in the constellation diagram. This is the OFDM symbol to be transmitted, and these are the learning curves, that is the mean square error plots with iterations. We see that all of them converge, hence the algorithm is stable, and these are the error square plots. Now we will have a look at the performance of RLS algorithm. The initial part of the code is same as that for LMS. The RLS algorithm can be seen in this part where we construct the autocorrelation estimate as a memory weighted sum of previous estimates of the autocorrelation matrix. We have the forgetting factor to be chosen as 5.5, and we perform the RLS algorithm, and this is the normalizing step while obtaining the impulse response estimate from the U subscript W matrix. The initializations are same as that for LMS algorithm. The impulse response, the R matrix, all are initialized randomly with uniform random distribution. And we will get the following results when we run this. This is again a plot of the lens, number of symbols that are being transmitted. This is again so here we obtain the plots of the error square, and this is the plot for the mean square error as it varies with every iteration. So this again shows that the mean square error will, when compared with the LMS technique, is lesser, but when compared to the speed of convergence, LMS algorithm is much faster. This is the OFDM signal to be transmitted, and that is it. Thank you.